Okay, so in this clip, we will talk about the pair of infinitely long wire. Okay, so firstly, we are considering an infinitely long wire. As we have seen from the calculations using Biot-Savart laws or the Ampere's law. Okay, if I have a wire, an infinitely long wire of current I1, for example, what we should come up is that is going to be the magnetic field, in the direction along with the right hand rule. So suppose that if I represent the current by the thumb, the direction of magnetic field will be in the direction of my fingers. Okay, so that if I try to write magnetic field direction down in this nomenclature, okay, so the magnetic field at the location upper, okay, from the current line will be pointing out from the screen, okay, and on the location under the wire will be pointing into the screen, and the magnitude of the magnetic field at the distance, let's say d, at the distance d from the wire will be according to Biot-Savart or Ampere's law. The magnetic field B1 from the current I1 will be mu 0 I1 over 2 pi d. Okay, so that we can conclude that I1 can generate B1 in these directions and this magnitude. And after I1 generates B1, I'm going to put another current line, another wire that carrying current I2. So then I2 here will be placed within the magnetic field of B1. So we're going to say that 2 is affected by B1. So the force acting on I2 will be I2 times L times the length and times by B1. And if I substitute the B1 into here, I will have I2L times by mu I1 divided by 2 pi d. Okay, so that I'm going to have, so we rearrange it. I'm going to have mu 0 I1 I2 times L and divided by 2 pi d. Okay, so this is in the case that L is longer and longer than d. So if L is very long and if the distance d is very narrow, okay, we have these equations. Okay, and according to actions and reaction, or Newton's third law, okay, what we have is we are going to have F1, okay, which is the force acting on the wire number 1, okay, and with the same magnitude but different direction. Okay, so the direction of I1 and I2, okay, we can use the right hand rule to determine the direction. Okay, so firstly let's start with I2. Okay, for I2 we have the direction of I2 represented by my index finger, and I have the direction of magnetic field represented by my middle finger. So this is B. Okay, so the vector B and the direction of I1, which is correspond to the vector L of the displacement. So that the force can be calculated from the cross product of L and B. So that I will have the force F, okay, in the direction represented by my thumb. okay, according to the right hand rule. So F is going down, F2 is going down, okay, and with the action equals reaction stuff, okay, if 2 is affected by 1, so 1 is also affected by 2 by the action equals minus reaction. So the force acting on F1 will have the same magnitude but in a different direction. So that we conclude that in this case of infinitely long wire with current I1 and I2, so if current is going in parallel or in the same direction, this causes two wires to be attracted to each other. So they come together, okay, by the magnetic field of each other. But in the same story, but if we try to consider the I2 that goes to the opposite direction to I1, okay, and try to apply the right hand rule to this case, okay. So I have the vector L that is representing also the direction of the current, and I have the direction of magnetic field pointing out. Using the right hand rule, okay, so we do cross product of L and B, okay. We should represent the results of cross product by the thumb, and when the thumb is going up, okay, in this case I have F2 or F acting on the wire number 2 as this vector, which is in the up direction, and from actions equal reactions, okay, we have F1 the same magnitude but opposite direction, so I have F1 going down. So in conclusions, okay, so as we have parallel current, parallel current will make the two wires attract, and then the anti-parallel currents mean that if one go to the right and if another one go to the left, the wire will be repulsing each other.